In this video, I will talk about electronegativity and explain its effect on bond polarity. Electronegativity measures the element's ability to attract bonding electrons. So more electronegative elements have higher tendency to attract electrons than less electronegative ones. Electronegativity increases as we go from left to right in the periodic table and as we go up. In this table, we can see some of the electronegativity values of some of the most common elements. Fluorine is the most electronegative element, followed by oxygen, chlorine, and nitrogen have the same electronegativity. Then bromine, followed by carbon and sulfur and iodine. They all have the same electronegativity. So what is the effect of electronegativity on covalent bonds? Electronegativity difference leads to something which is called bond polarity. If we have a covalent bond between two similar elements or two elements with very close electronegativity values, then the bond will be considered as a non-polar bond. Why? Because we have a uniform electron distribution between the two elements. So the shared electrons which are between those two elements, because we have similar electronegativity values on both sides, they will be equally shared between the two elements, and that's why we have uniform electron distribution. So if I'm moving from this side to this side, I will notice that the electrons are uniformly distributed. However, if we have two elements such as hydrogen and chlorine, which have big electronegativity difference between them, in this case, chlorine, because it's highly electronegative, it will shift, it will attract electrons, those electrons which are here, to move toward its side. And that's why if I'm moving from this point to this point, I will notice that next to hydrogen we have low electron density, whereas when I move to chlorine side, I will notice that we have high electron density. So electrons are actually concentrated at chlorine side because it's more electronegative. Because of this, hydrogen will have a partial positive charge, as if it lost electrons, and that's why it's partially positive. And chlorine will have a partial negative charge because as if it has gained some electrons. So since we have positive and negative, the bond will set to be polar bond, and we can draw a polarity vector which starts from the less electronegative element toward the more electronegative element. So bond polarization is a result of the electronegativity difference between the bonded elements, and this leads to shifting of electrons toward the most electronegative, as we saw here in the case of chlorine. And this leads to the creation of high and low electron density regions, and in this case the bond is said to be polar and to have a dipole moment. These are called electrostatic potential maps, and they give us an idea about the electron distribution around the elements. As you can see here, in hydrogen and hydrogen, we just have one color, which is this yellow color, and this is telling us that basically we have uniform electron distribution. In case of hydrogen fluoride, because fluorine is by far more electronegative than hydrogen, then most of the electrons will be shifted toward the fluorine. How is this affects the color? We have a red color here, and the red color means high electron density, and we have a blue color here at the hydrogen side, and this means that we have low electron density. So the electrostatic potential map tells us or shows us where are the electrons highly concentrated by expressing this in the form of a red color, and the region with low electron density will show up as a blue color, and this again proves bond polarization. If we have a fluorine-fluorine bond, since we have similar elements Again, we just have a yellow color, which is telling us that we have uniform electron distribution and there is no bond polarization. The dipole moment is the product of the charge E by the distance d, and it is measured in dBys. And it's basically an equation that is used to tell us how polar is the bond compared to other ones. 1 dBi is equal to 10 to the negative 18 electrostatic units times centimeter. For example, the hydrogen fluoride bond is 1.7 dBi HCl. Because chlorine is less electronegative than fluorine, the bond will be less polar, so the dipole moment will be less. Even less for hydrogen bromide or hydrogen iodide, because as we are going down from here, from F to I, electronegativity is decreasing. So the electronegativity difference between hydrogen and the other element is decreasing, and that's why the bond polarity is decreasing. So as the dipole moment decreases, this means that the bond is less polar. Again, if we compared carbon fluorine, carbon oxygen, carbon nitrogen bonds, we can see that the dipole moment is decreasing because of the decrease in the electronegativity difference. The presence of a double bond. So if you compare the carbon oxygen single bond and the carbon oxygen double bond, you can see that the bond is more polar in this case, and this will be explained later on based on the hybridization effect. So how do we draw the polarity vector of a polar bond? You just have to compare the electronegativity of the bonded elements and draw a vector by moving from the less electronegative element toward the more electronegative one. So, for example, in this case, oxygen is more electronegative than hydrogen, and that's why when I want to draw a vector, I will draw a vector starting from hydrogen toward oxygen. Remember that the vector always starts from the less electronegative element toward the more electronegative one. Hydrogen will be partially positive and oxygen will be partially negative. Again, carbon and oxygen here. Carbon is less electronegative than oxygen, so the polarity vector will move from carbon to oxygen. This is partially positive, this is partially negative. Carbon fluorine bond. Carbon is less electronegative than fluorine, so the polarity vector will be from carbon to fluorine. This is delta minus, this is delta plus. High electron density at fluorine, low electron density at carbon. Same thing for carbon and nitrogen bond. Carbon is less electronegative than nitrogen, so the polarity vector will be from carbon toward nitrogen. This is delta positive and this is delta negative. So this is how we draw the polarity vectors if we have elements with different electronegativity. Now sometimes if the electronegativity values are very close to each other, such as in the case of carbon and hydrogen, in this case the bond will be considered as non-polar, even if we just have a small difference. But since it is very, very small compared to the other ones, then the carbon-hydrogen bond is considered as a non-polar bond. And the same thing applies for other elements with similar electronegativity values.